And the final question in this section, we've got the atom beam now incident on a diffraction grating, which is different from a double slit. Remember, you can't apply the small angle approximation for the diffraction grating because the angle of diffraction is much wider. Anyway, that's kind of irrelevant because if you're following on from the previous questions, you'll just use that formula, but it's good to be aware of these things. So I'll just write that down. Actually, the formula d sine theta equals n lambda still applies. If the energy range to delta E, so remember that's plus or minus delta E, which means the range is going to be twice that, plus and minus gives you the full range. The interference fringe of the first order maximum will overlap the second order maximum. Let's draw a quick diagram to try and show this. We should get this clear in our mind before. We've got a diffraction grating, lots of gaps over here. We've got our atom beam incident on there, and then it diffracts to, through particular angles to produce intensity maxima with again your 0th order, your first order, your second order, and so forth. And same on the other side, first order, second order. You'll have an E value, your energy, kinetic energy, remember, of the atoms that are incident, so because it's an atom beam. And again, that might sound strange that you have atoms diffracting, but the atoms and the mass itself has a wave function, the molecule, and acts like a beam of light. So we take that wave function, find an angle it deflects through, and so that energy that produces that particular wavelength of atom will have a range, and this is where the key of the whole thing lies. That range will be plus E to produce an angle somewhere up there, and minus E, or delta E, let's be precise, to produce that potential range. So you're with your maximum possible range of E, you're going to get an intensity maxima that's not very distinct, but it's spread across the entire range, right down to when the next one starts. So you've got another E value here, and you've got another plus a certain amount of delta E to get up to there. And we don't want those to overlap. So the actual question says derive an expression for delta E, which means delta E equals something, such that the first and second fringes have no overlap. So we don't want them to overlap. Okay, as I usually say when dealing with these scholarship physics questions, the hardest battle, or the most difficult thing, is interpreting the question and understanding it, and that can set you off. If you get it wrong, it can set you off on a wild goose chase, and if you get it right, it can often be the difference between making a question only take a few moments or a few minutes, rather than taking ages and ages and giving you lots of mental stress. So what we might like to do to look at this question, before we get too carried away, we do have an alternative expression for this in terms of E. Remember, it was d sine theta equals n, and it was the Planck's constant divided by square root of 2m E. So this is going to be the foundation for our expression for delta E, where there's no delta E in there at the moment, but what we're going to have is two E values. Let's just go back up to the question, because there's an important piece of information we might have forgotten. It's an expression for the first and second fringes, so that's n equals 1 and n equals 2, and we don't want them to overlap. So what might be a good idea is to rewrite this formula for n equals 1 and for n equals 2. Remember, the n equals 1 formula, we should probably add on, because that'll increase the angle, delta E. and for n equals 2 we want to take off delta E because it'll decrease the angle, and that'll give us, going back up to our diagram, writing in blue over the top, we've got the n equals 1 line plus delta E up to somewhere here, and then we've got the n equals 2 line minus delta E, and we don't want them to overlap, so they have to be fixed and clear. So let's just work through putting those into a formula and see what we come up with. So for the first one, where n equals 1, we're going to have d sine theta equals n is 1, so 1 times h over square root of 2m, and we've got to put brackets here because it's e plus, where are we, plus delta E. So now we've introduced this delta E into the whole equation. It's starting to look a little bit big and tricky, close our brackets, but it's really just a slight modification from the earlier expressions we've used. So that's for n equals 1. Now for n equals 2, we've got d sine theta equals 2 times h divided by the square root again of 2m, and this time it is e minus delta E. Okay. Now you might be a little bit concerned over theta being the same in this case, because one is for n equals 1 and one is for n equals 2. But remember, we're after that boundary condition where we're mostly concerned right here with, let's draw yet another colour over the top because it'll be easier to see. Striking right at that boundary there, we're going to have an angle of diffraction which exactly meets, for the n equals 2 situation, minus delta E, and for the n equals 1 plus delta E. So the angle is actually going to be the same. It's the angle right at that boundary. And that's so E has to be, or delta E has to be equal to that but not greater than that, otherwise they'll overlap. Sorry, delta E has to be equal to or greater than whatever we find out with this theta. So theta is the same, and that does make things remarkably easy for us. It might not seem so just yet, but we can be sure that theta is the same. Let's just write that in so we don't forget. So those two are the same as each other. That means that the two right hand sides, this is equal to this. So we can just put those two together side by side in an expression and do some calculations to bring them through. Now we'll notice that quite a bit of this is going to cancel out. So I'm going to rewrite this with everything cancelled out. Everything that can be cancelled out we will cancel out. And you can work through later to make sure that I haven't included any cancellations that shouldn't. Hopefully we'll come to the right answer, and that'll tell us anyway. H can cancel out. So if we do the left hand side, is going to be this one here. We're going to end up with 1 over, now 2m is the same for both, so we can ignore the square root 2m part. So let's just worry about the square root E plus delta E. That's the left hand side, nice and easy, and that means the right hand side is 2 over square root E minus delta E. So this is really good. Our expression is, we're looking for delta E, and it's going to be in terms of E. It's going to be a very, delta E as a function of the energy, which should make it quite easy for us to follow through. So if we cross multiply, we're going to end up with 1 times, let's just show you what I mean by cross multiply, because you might not be familiar with that style of notation. 1 times that will bring this, will help us to cancel that out, and then 2 times that will help us to cancel that out, and they'll equal each other. Excuse me. So we end up with square root e minus delta e equals 2 square root e plus delta e. Okay, this is looking a little bit easier. Now we can square everything to remove those awkward square roots. So this on the left hand side will be e minus delta e. On the right hand side it will be 2 times e plus delta e. Okay, and again on the right hand side 2e plus 2 delta e. And then just following it all the way down, that means, where are we, of e minus delta e. When you're following big long calculations, it's a really good idea to put in all the steps exhaustively, otherwise you can get tripped up without realizing it. So I want to shift the delta e's onto one side, and I want to put all the e's onto the other. So we're going to, what are we actually after? We're after delta e by itself, so let's move the delta e's to the right hand side. So we end up with, and the e's to the left hand side, so we end up with minus e equals 3 delta e. Did I do that right? I've just realized I've made an error, and you might have even spotted it, but I forgot to square my 2 as well, so that should be 2 squared, which means that should be 4, and that should be 4, which means that this will be on the left hand side we will have minus 3e, and on the right hand side we will have plus 5 delta e, positive 5 delta e. Okay, so continuing our rearrangement, because we want to get delta e by itself, we end up with, this is just divide by 5, both sides by 5, delta e equals minus 3e over 5. So we've got an expression now for the change in energy that we can have in terms of E, and that almost answers the question. We're not completely there yet. There is one part missing, and that is, remember, this is the expression for delta E when it is going all the way back up. This is the expression for delta E when it is right at that boundary. For it to not overlap, delta E has to be less than what we've just found out. So let's go all the way down, and our final step, sorry, not just less than, it should be less than or equal to. So we're going to do this. That is a legitimate expression, and I think that's what we'll find in the solutions. Delta E is less than or equal to minus 3e over 5. So fantastic, very long, tricky calculation. Starts off with you setting it up really carefully.